All right, we finished chapter 14 here in part 5 with a discussion of the only other type of NMR that we will use in this class, which is carbon NMR. Okay. Now keep in mind there are a ton of things that are NMR active. There are other kinds of NMR out there. Videos 1 through 4, we talked about proton NMR. Here we're talking about carbon-13 NMR. Because normal carbon, carbon-12, is not NMR active. It's 6 protons, 6 neutrons. That's even and even, the one thing that isn't NMR active. So we need, in order to distinguish carbon in NMR, to use carbon-13. Okay? So it's harder to distinguish these signals due to the fact that only 1% of all carbon is carbon-13. Okay? Once we can do it, okay, it's more difficult to acquire. Okay? It requires a computer for the FT process, Fourier transform process. It takes longer to do. Okay? These are really weak signals, so typically the experiment's repeated several hundreds of times in order to distinguish signals from the background noise. But when we can get carbon NMR, it does have really useful information, because the number of signals that we get, the number of peaks, reflects the number of different kinds of carbons we have, just like proton NMR. It goes over a much broader range of ppm, right? Proton NMR was 0 to 12. Here we're going 0 to 220. Okay? So that much greater range makes it a heck of a lot easier to identify different carbons. Okay? And we still use the same reference compound, tetramethylsilane. All right, so with carbon NMR, right, we have a chart of clear different ranges where different kinds of carbons appear, which this will be really useful for your homework. And then you also have the quick and dirty approach, right? 0 to 50, saturated carbons have bonded to something more electronegative that's not oxygen, around 50. 50 to 100, okay, your alkynes or your carbon oxygens. 100 to 150, your double bonds, and then anything above that, a carbonyl. So really easy to distinguish different carbons here. This is what an NMR spectrum looks like, right? Still a plot of intensity versus frequency, still ppm on the bottom. Okay. Here for butanol, we've got 4 different carbons, so we get 4 different peaks. Okay. Again, this one over here is for TMS, the reference compound. Now, what's different about carbon NMR is notice there's no integral here. Right? Because the area under the signals is not proportional to the number of carbons producing the signal. So we don't do integrations, right? We just do 4 signals on carbon NMR, tells me I have 4 unique carbons. There are some factors, right? If it's got a substituent, is it electron rich, is it electron poor, that can affect the signal frequency. And so carbons kind of get the same pattern as hydrogen in terms of where they're appearing. And we also notice everything here is showing up as a singlet, right? We don't have any splitting to worry about because it's just statistically improbable. Keep in mind, this is dealing with carbon-13, and the chance of having 2 carbon-13s right next to one another to split is, incredibly low. Okay. And while you could set it to couple with hydrogen, that is one method, it's typically not done. This is usually all we're saying with carbon NMR, 4 peaks, 4 unique carbons. If you did want to get some information about the hydrogens, you can do that. It's called a proton coupled carbon NMR spectrum. So we've now coupled, told the computer to couple the carbons to the hydrogens, 2 different types of nuclei. It's called heteronuclear coupling. And what this will do is split the carbon NMR peaks based on the hydrogens that they're directly bonded to. Yeah, so take D, for example, the one that's furthest upfield. Carbon here bonded to 1 hydrogen, right? Follows the n+1 rule, so 1 + 1 is 2. So that's why signal D appears as a doublet. Yeah. So, just not nearly as useful as proton NMR, but it does give us some valuable information. One other thing to keep in mind, if you don't have any hydrogens attached to a carbon, right? You've got a quaternary carbon like C right in here. That's going to give you a very small signal. Yeah, look at how small that signal is right there. Okay, this is A, B, C, D. Your methyl groups on B give you a really large signal because they're all identical. So that's pretty much the gist of carbon NMR. There's more of these to practice in your book. I recommend you take some time and look at those spectrum, see what information you can get. But the number one thing is just telling you how many unique carbons you have. Keep in mind 2 identical carbons, right, like we have here, because all of these methyl groups are identical. They're only responsible for 1 peak. So we finish by seeing what else we can do with NMR, which is usually the world, just the world of fun acronyms, and then a brief discussion on X-rays. There is a technique called DEPT, right? Distortionless enhancement by polarization transfer, DEPT. Okay? That's a way to do carbon spectra that's a little more common than proton coupling, because it will distinguish your methyl groups, your methylenes, and your CHs, excuse me, your methynes. And it does that by acquiring multiple spectra for the same molecules under different conditions. So it's not just going to give you all carbons, it'll tell you how many CHs, how many CH2s, how many CH3s. And so that's from DEPT. We've got COSY, 2-dimensional NMR, right? So now we're running it on multiple axes here. So it's proton-proton shift correlated spectroscopy, COSY. And so now we've got 2 frequency axes and 1 intensity axis. So a stack plot here on the left, a contour plot on the right. It's really useful for complex molecules, larger things like biologically active molecules, proteins, nucleic acids, etc., because it tells us protons that are coupled without actually having to go in and measure coupling constants, and it does that with the cross peaks. We also have HETCOR, heteronuclear correlation spectroscopy. This is where we have carbon and proton shifts correlated with one another. Tells us what hydrogens are attached to what carbons after acquiring both spectra, kind of putting 2 ideas together. And here we see some other techniques as well, nosy, rosy, and inadequate. I told you some of these acronyms get ridiculous. These first 2 tell us proximity of hydrogens to one another, and 3D tells us inadequate, tells us carbons that are directly bonded to one another. But these tend to only be necessary for really complex molecules to figure out how they're folding, for example. And none of these I would expect you to know for a test, any of these department or COSY or HETCOR or nosy, rosy, inadequate. And remember that even though we've gone through 89 slides here, you already knew what NMR was, probably under a different name. Okay? MRI, which, in the hospital, magnetic resonance imaging, is NMR of the body. It just goes under a different name because people tend to be afraid of the word nuclear, think it's scary. Okay? And in an MRI, it's using NMR and taking advantage of the fact that different tissues give us different signals due to the way that water is bound, right? Because we're typically looking at the signal of water to provide an image of your internal serum. You typically get an MRI with a contrast agent, something like gadolinium, because it can alter the surrounding magnetic field and will behave differently around things like cancer cells or tissue that's inflamed. That's NMR of the body. Okay, neat stuff. That's what an MRI looks like medically, and then this is spectrum that indicates different abnormalities with the body. So as I mentioned, we finished with a 30-second discussion on X-rays, just kind of thrown in the end of chapter 14, X-ray crystallography. The nice way to determine unit cells. Right, the arrangements of atoms within a crystal structure. You have to have a crystal that's at least 0.5 millimeter cubed. You can use X-ray crystallography to tune the wavelength to the distance between the atoms. It produces a diffraction image. Right? It's called X-ray crystallography because the wavelengths are falling in the X-ray region that you use. It shows you the electron density from the bonds. Any 2 regions of electron density within bonding distance are assumed to represent bonded atoms. You take this X-ray spectrum, do a buttload of math with it, and you can actually solve crystal structures from this. This was pioneered by Dorothy Hodgkin right? And Rosalind Franklin, who you've heard about for DNA. And I think the text just tosses it in at the end of chapter 14 there, because that's yet another portion of the electromagnetic spectrum, X-rays, that we're taking advantage of for imaging. We did mass spec, then we talked about IR in the infrared region, then we talked about UV vis, right, ultraviolet visible, NMR, radio waves, and now X-rays. All different portions of the electromagnetic spectrum that we can use to garner information. Yep. Nothing here that would be tested. I certainly wouldn't expect you to take, get any information from that type of plot. It has its role for crystals. Unfortunately, in organic, we don't work with those all too often. So that concludes chapter 14. The big takeaway from this video is carbon NMR, taking the information that it gives to you, knowing what to do with it, because in the future, you'll be asked to put all of these pieces of the puzzle together. Given a mass spec, an IR, a proton NMR, and a carbon NMR, can you determine a structure? That's the challenge that you're faced after chapter 13 and 14. Taking all the pieces of the information together, it's just using logic to solve a puzzle.